Hi, here we present our work on lightweight vision transformers for low-energy edge inference. To give some background, vision transformers are encoder-only models for computer vision tasks. These models are of interest to us as they are state-of-the-art in image classification tasks for some datasets. However, the primary issue with it is that it's quite resource-intensive. Particularly, they have large model sizes that scale quadratically with the latent dimension, have high hardware resource requirements, both in terms of compute and memory, as could be seen in the tables here, have high latency, and involve power-hungry multiply accumulate operations. All of this makes these vision transformer models inefficient for edge inferences. Weightless neural networks are a different class of neural networks that are based on lookup tables. While an artificial neuron, as shown on the left, has inputs being multiplied by weights and added to biases, a binary neuron found in a binary neural network extends this to binary quantized weights and activations, leading to XNOR and summation operations. In contrast, in the case of weightless neurons, the input bit sequence is concatenated to form an address that is then looked up in the lookup table to give the output of the neuron. This effectively eliminates the multiply accumulate operations. At the same time, these LUT-based neurons are also efficient to be deployed on FPGAs, owing to the underlying logic on them being LUT-based. Weightless neural networks, or WNNs, are networks of such weightless neurons or lookup tables. Against iso-accuracy multi-layer perceptrons, or MLPs, these WNNs have smaller model sizes, significantly lower hardware resource needs, lower latency, and lower energy consumption per inference. This makes WNNs extremely suitable to be deployed for low-latency inference tasks. However, when evaluated on image classification tasks, though WNNs perform pretty well on small datasets, they perform poorly on even slightly larger datasets like the SIFA-10. Now making a direct comparison between vision transformers and WNNs. VITs have high resource utilization, high latency, and are power hungry, while WNNs involve low latency and are energy efficient. With VITs, model sizes scale quadratically with latent dimensions, while they could potentially be scaled linearly in case of WNNs. VITs are complex models that have proven to be performing pretty well on complex datasets, whereas WNNs, on the other hand, are simple models and perform worse on larger datasets. Through self-attention, VITs could possibly learn positional relations across the image, while no such features exist with the WNNs. We note that linear layers form a major chunk of VITs, and interestingly, WNNs compare well with linear layers. All of these point to suggest that WNNs and VITs are kind of complementary, and it would be worthwhile to see if these could be combined together. This brings us to the idea of weightless vision transformers, which combine aspects of transformers and WNNs. We propose to fuse and replace some of the linear and nonlinear layers in the transformers with weightless layers, thereby resulting in reduced power consumption and latency at the cost of potentially lower accuracy. To answer the question of why specifically transformers, we are particularly interested in exploring transformers as we eventually aim to extend these weightless models to language models. And while other alternatives exist for vision tasks, transformer-like models are ubiquitous in the language model realm. Also, vision transformers serve as a good stepping stone in that direction, as they are architecturally similar, while also being easier to work with owing to smaller datasets and smaller model sizes.
We profile layers in the vision transformer model and figure out that the MLP layers in vision transformers are quite compute and memory intensive, with these taking up about 57% of total MAC ops and about 66.7% of total model weights. Some past studies show that weightless layers outperform ISO-accuracy MLPs in terms of reduced energy consumption and latency. With that background, we propose to replace these MLP layers with equivalent weightless FC layers. We hypothesize that this would lead to energy savings offered by WNNs clubbed with the performance advantages of transformers. We adopt the following methodology for our study. We first design a weightless layer suitable for integration into a larger model. similar to one proposed in ULEAN and DWN. We then design a quasi-weightless model replacing MLPs with these weightless layers. We train this model, tweak hyperparams, and report accuracy. We then use analytical models for the hardware resource consumption, energy, and performance, and then iterate over the above steps, incorporating feedback from these analytical reports. We note that the prior weightless neural network models were primarily discriminator-based. However, since we design a model in which the weightless layers are intermediate layers in a larger network, we need to ensure that these preserve the latent space dimensions. Keeping this in consideration, we redesigned the weightless layer with inspiration from prior works, including ULEAN and differentiable weightless neural networks, DWN. Now, looking back at the vision transformer model, we replaced the MLP block in each layer with the designed weightless layer. The resultant network, that we call the quasi-weightless vision transformer, looks like this. The particular weightless network that we replace in this study include 2 layers of lookup tables, followed by a summation layer to generate outputs that preserve the latent dimensions. We note that the input activations are flattened out and passed row-wise to the network in order to ensure that it maintains the independence across the tokens, as is expected out of the MLP. We redefine the PyTorch models for these quasi-weightless models and go about the training routine. We pick the transformers pre-trained on ImageNet and fine-tune it on Cipher10. We then substitute the MLP layers with the weightless layers and then train the entire model. We iterate over different weightless layer configurations and training strategies.
We primarily report our model accuracy evaluations on 2 variants of the vision transformer model. When evaluated on the Cipher10 dataset with the I-ViT-T tiny model variant, the quasi-weightless model reports a top-end accuracy of 89.44% against a baseline of 95.41%. On the DEIT tiny model variant, the quasi-weightless model reports a top-end accuracy of 80.3% against a baseline of 87.1%. Thus, the quasi-weightless models report a drop in accuracy of about 6 to 7%. We also note that these models perform much better than prior fully weightless models, such as ULEAN, that reports an accuracy of about 54%. In order to perform hardware evaluations and compute performance improvements, we consider an experimental setup with the Pink C1 FPGA board. We design RTL modules that correspond to each of the operations performed in the I-ViT tiny model shown here, including the matrix multiplications and the nonlinear blocks, including Shift Max and Shift GLU. We synthesize these on the target FPGA to extract the hardware utilization and power reports. The MLP block being replaced here is shown by the dense Shift GLU dense bubbles. We identify the dimensions of the matrix multiplications of interest to us and design a systolic array-based accelerator that's typically used in literature for MLP accelerators. We use this to consider hardware estimates for our baseline and also design a high-throughput inference accelerator for the introduced weightless layers similar to the ones proposed in ULEAN and DWN. In addition to the systolic arrays, we also created a dedicated processing unit for computing the Shift GLU and Shift Max operations. If we compare the hardware performance of just the MLP layers that are being replaced, we see a significantly high improvement of the weightless layer over different systolic array matrix multiplication implementations of the MLPs. Particularly of interest is the huge savings in energy per sample inference, down from about 62 microjoules in the best case to 1.99 microjoules for the weightless network, as shown in the table here. With those preliminary reports from the synthesis, we extrapolate these numbers to arrive at the end-to-end performance comparison numbers. We consider the best case scenario of a 32 cross 32 systolic array multiplier from the previous table for comparison. We note that the major energy contributors, that is, the 2 matrix multiplications in the MLP and the Shift GLU, are replaced with an energy-efficient weightless layer, thereby resulting in an overall energy savings of over 65%. The key limitation that we note in our work is a drop in model accuracy, and that would be our primary focus going forward. We aim to optimize the weightless layers to improve the overall accuracy within the hardware budgets. In order to do so, we plan to incorporate learnable mappings from DWN and knowledge distillation from MLP to the weightless network, among other techniques. We also plan to extend our evaluation on additional transformer model variants, tasks, and datasets, and compare these against other bindarized models. We then plan to extend this concept to the weightless self-attention layers, aiming for a fully weightless vision transformer. Eventually, we also look to extend this to decoder-only and encoder-decoder models, thereby paving the way for large language models. From our study, we make the following conclusions. Primarily, we show that integrating WNNs and vision transformers is a viable option, and it is a promising lightweight alternative to the traditional vision transformers. These quasi-weightless vision transformers also perform much better than prior weightless models. These models achieve significant energy savings traded off by a drop in accuracy. On the I-ViT timing, these are projected to achieve a 2.9x savings in end-to-end energy efficiency for a 6% drop in top-win accuracy on Saber 10. We also eliminate the BRAMs in the MLP layer, which account for nearly 60% of the overall BRAMs in the model. What this also means is that we save the energy involved in fetching weights from off-chip memory, which is usually a higher contributor. We also note that we are working on employing better training strategies to close the gap in accuracy while maintaining hardware efficiency.